Welcome to the second half of this week's material. The previous lesson concluded by describing population parameters and sample statistics. Now we spend a little time talking about a field of statistics called descriptive statistics. Descriptive statistics refers to the branch of statistics that aims to tabulate data through graphical means or to calculate a descriptive measure. Simply, this is trying to summarize a set of samples. If you remember, we talked about the mean and standard deviation. These are descriptive statistics that can be used to characterize a sample. The goal of descriptive statistics is to capture some aspect of a sample through a single value. A common and very complicated place many of us are used to seeing descriptive statistics are in football quarterback passer ratings. This number summarizes many aspects of the quarterback's performance into a single value. Since we have such a wide variety of ways we can try to describe a characteristic of a sample, statisticians have provided some guidance to consider when choosing a descriptive statistic. The main thing to keep in mind is that we want a statistic that will provide similar results if we took multiple sets of samples from the same population. It should also be something that people can easily understand and that will not be overly influenced by an extreme value. Now we will spend a little time talking about how we can actually describe a sample. Biometrician Kim Miles may have described this best. Inventory is a process embedded in larger processes. Ignore this at your peril. The principles of sampling do not change over time, and there are a few really revolutionary new ideas. Nobody masters the basics of statistics because they are smart, only because they are persistent. An inventory is the process we use to actually collect data from a population. But the inventory itself is only a small component of what goes into sampling. After we lay the underlying statistical principles of sampling, we can use this knowledge to design our sampling strategies. Generally, there are 3 levels to describing a population. We will focus on the first 2 levels. However, it is important to remember that the third order of descriptive statistics, focusing on the skewness and kurtosis, or the shape of distribution, are very important when it is necessary to understand the structure of the population's distribution. The first way we try to describe a population is using measures of central tendency. These statistics are used to describe what we refer to as the location, performance, or center of our data. The first and probably most common measure of central tendency we will look at is the arithmetic mean. We talked about this one in the last lesson. In Excel, we calculate this by using the equals average function with our data selected inside the parentheses. Along with the arithmetic mean, we often describe the median and mode of a dataset. The median describes the midpoint within a dataset such that half of the values are above it and half of the values are below it. The mode is the value that occurs most frequently in the dataset. When the values are considered together, they can give us a simple way of assessing skew or normality within the dataset. Where the values are similar, the data is normal, but if the values differ from each other, the data is considered skewed. A value we use less often, but will utilize when talking about stratified sampling, is the weighted mean. This metric applies a measure of importance to each sample, increasing or decreasing a value's importance to the overall value. A measure we will not use in class but is very important when looking at rates of change, such as growth rates, is the geometric mean. Commonly, datasets that this is used for fall on an exponential curve. The final measure of central tendency we will look at is the quadratic mean, which is not a typical average, but rather describes a measure of variability about the arithmetic mean. A common use of the quadratic mean is the quadratic mean diameter in forestry, which describes the diameter of the tree of average basal area. The quadratic mean has a special relationship to the arithmetic mean. Not only will it always be larger than the arithmetic mean, but they will follow a relationship that can be described by the Pythagorean theorem. Whereas the standard deviation of a dataset increases, the difference between the arithmetic mean and the quadratic mean increases. Although we will spend a lot of time understanding measures like the standard deviation, it is important to remember nobody ever bought or sold a sampling error, and nobody ever made a dollar knowing the statistics. The average or total of something is everything. We may need to spend a lot of time understanding these other descriptive statistics, but that is because they are trickier to understand, not because they are the most important topic. In the end, it is usually the average or total which matters more than any other number. The second set of metrics we use to describe a population are measures of dispersion. These metrics describe how much individual samples differ from the arithmetic mean. We will look at a number of these metrics, but it is important to remember that they are simply trying to describe the variability of items in a population, where variability is a way of describing the range of possible values that individual samples could have in a population. The first and most commonly used measure of dispersion is the standard deviation. We can describe this for the population as the average of the squared deviation from the arithmetic mean, where the denominator is big N. We can only calculate this when we have conducted a complete census of the population. Since it is rare that we conduct a census, we must substitute our sample mean into the formula. Also, since we are using the sample mean, which is known to differ from the population mean, we have to account for this difference, and we do so by substituting little n minus 1 for big N in the denominator. To calculate the sample standard deviation in Excel, we use the equation equals stdev dot s with our data selected inside the parentheses. The other very important measure of dispersion is the coefficient of variation. Let us think of a situation where the units of measure do not mean anything to us. Same when stream flow volume is plus or minus 1.6 firkins per hour. Could you tell me, is that a lot or a little? However, if we can express the variation in percentage, say plus or minus 4% of firkins per hour, the statement becomes much more interpretable by a broader audience. Another way to think of this is the standard deviation in percentage form, where it is equal to the standard deviation divided by the mean. Now this can either be expressed as a decimal, such as 0.3, or as a whole number, like 30%. Unfortunately though, Excel will not actually calculate this directly for us. When we square our standard deviation, or remove the radical from its calculation, we change its name to variance. Although many calculations call for variance, its units are difficult to interpret. Its statistical symbol is theta squared for a population and s squared for a sample. Because of the units variance has, you will almost certainly report a standard deviation or coefficient of variation instead of the variance itself. The reason that variance's units are weird is because we are calculating the squared deviance. and it is that squaring that is changing the units. I have always enjoyed the physicist Richard Feynman's writing, and believe this quote captures how I like to engage with my students. There is no harm in doubt and skepticism, for it is through these that new discoveries are made.